Hello guys, welcome back to EC TechNest. In this lecture, we'll continue with the filter mask components. That is, the matrix value should be written in such a way that on performing addition, the final result should be 0. That is, when you add all the positive ones, you will get +4, and on adding with -4, you will get the value 0. Similarly, -8 is surrounded by 8 plus 1s, and hence the final result will be 0. You have to write the Laplacian filter design in such a way that the sum of the mask coefficients will always be equal to 0. Considering the diagonal elements also, we have to construct the mask. So the next one is the middle value, that is z5 is f of x comma y and z6 is f of x comma y plus 1. Similarly, z3 is f of x comma y plus 1 and f of x minus 1 comma y, f of x minus 1 comma y minus 1, as well as f of x comma y minus 1 and f of x plus 1 comma y minus 1. And delta square f of x comma y is equal to f of x plus 1 comma y plus f of x minus 1 comma y plus f of x comma y plus 1 plus f of x comma y minus 1 minus 4 into f of x comma y. This we have derived in the previous video also. So this is how we illustrate Laplacian filter. First one is the blurred image of a north pole of the moon, and the image B represents Laplacian without scaling, and image C represents Laplacian with scaling, and the final image represents the result of using the mask values from the original. Next, we will be discussing about the unsharp masking and high boost filtering. So in this, we are printing and it is mainly used in the printing and publishing industry for sharpening the images. So first we are originally making the original image blur, and then performing smoothing operation on original signal which is having very sharp intensity transition. So blurred image is subtracted from the original image, and the resultant is the unsharp mask. Unsharp mask is added with the original image in order to obtain the sharpened image. Wherever there is sharp transition at the particular points, there the image has been enhanced, and this is the procedure to produce a sharpened image. In terms of the graph or the 1D illustration, so this is the original image and this is the blurred image. When we subtract original image from blurred image, we get the unsharp masking. When unsharp masking is again added to the original image, we get the sharpened signal. So f of x comma y is the original image, and fb of x comma y is the blurred image. You can write that as f bar of x comma y, and the unsharp mask is represented in the form of equation, that is g mask is equal to f of x comma y minus fb of x comma y. So unsharp mask is added with the original image in order to obtain the sharpened image. So next equation would be g of x comma y is equal to f of x comma y plus k into g mask of x comma y. If the value of k is 0, then it's unsharp masking. If the value of k is greater than 1, then it is high boost filtering. If the value of k is less than 1, also it is unsharp masking. So unsharp masking and high boost filtering is used to sharpen the image. Next is the original image. First one is the original image, and second diagram represents the result of blurring of the image. Third one, that is the C diagram, represents the unsharp masked image, and the fourth diagram represents the result of using unsharp masking, and fifth diagram represents the result of using high boost filtering. Next, we are using first order derivative for image sharpening. First derivative in image processing is implemented using the magnitude of the gradient, that is the function f of x comma y. The gradient of f at coordinates x comma y is defined by a two-dimensional vector. Delta f is equal to gradient of f, that is g of x and gx and gy, It is represented by dou f divided by dou x into dou f divided by dou y. Next we are finding the magnitude of the vector m of x comma y is equal to magnitude of delta f, which is the square root of gx square plus gy square. So this we have already discussed. Gx is equal to dou f divided by dou x is equal to f of x plus 1 comma y minus f of x comma y. That simply implies z8 minus z5, whereas gy is equal to dou f divided by dou y is equal to f of x comma y plus 1 minus f of x comma y, that is the z6 minus z5. So magnitude is obtained by square root of gx square plus gy square. Next is Robert cross vector. So first we have the gradient mask values to be minus 1, 0, 0, 1, and next one to be 0, minus 1, 1, 0. So this is obtained by the gradient equation gx and gy. To design the mask, we have to first sharpen the image using the gradient, and then no center symmetry in the cross gradient mask. So the smallest odd mask that is possible is 3 cross 3, and we also has Sobel mask. So this is how you represent gx is equal to dou f divided by dou x plus is equal to z7 plus 2 z8 plus z9 minus z1 plus 2 z2 plus z3. Similarly, gy is represented by z3 plus 2 z6 plus z9 minus z1 plus 2 z4 plus z7. So the 3 cross 3 matrix are obtained based on the intensity levels. So the figures B represents the Robert operators, and figure D and E represents the Sobel operators. In exam they'll ask question to apply or numericals directly to apply Robert and Sobel's operator in a given matrix. So this is the final expression or the magnitude of the gx and gy. Next we'll discuss about spatial filtering in the next lecture. Thank you.